welcome you all to the next interactive session on this transformer. So what we are basically going to do is to derive the practical transformer from the ideal transformer. So basically this is what an ideal transformer is going to look like. So it is having two windings, primary and secondary, connected to source and load respectively. Now, how I am going to derive it, the practical transformer? Ideally, what we know, that we assume that there is no resistance in the winding of the transformer. But practically, every transformer will have some finite amount of winding resistance. So that is to be included here. So we are having some resistance coming to play, and that would be there in both primary and secondary side. So let us suppose this resistance is R1, this is R2. Now, there is something called leakage flux in case of a transformer. So leakage flux is basically the flux which actually produced by the primary but doesn't link with the other winding, that is secondary. So both primary and secondary is going to have some amount of leakage of flux. So to represent that flux, actually we generally denote it by means of a reactance that we are referring it to as leakage reactance. So that would again would be in the primary and secondary. So since it's a reactance, we are denoting it by a coil. So we are calling it JX1 and JX2. Now winding is over. Then comes to the core of the transformer. Ideally, we consider that permeability of the core is infinite, which is we don't require any current to magnetize the core. But practically the core permeability will be a finite value, and therefore we require some current to magnetize the core. So for magnetization, we are considering that there is a coil JXM through which some magnetizing current is going to flow. Now when this current is going to flow from this magnetizing coil, some amount of flux is actually being produced, and then that flux will be flowing between the primary and the secondary winding. This is going to happen. Now in case of ideal transformer, we assume that there is no core loss occurring in a transformer core. But that might not be the case. There will have some core loss in a transformer. And generally we know that we are going to represent the loss as a resistance. So for that actually we are having some resistance over there that we are calling it RE, such that the loss occurring in this RE due to the path flowing of the current I through it will cause some loss, and that loss would be analogous to the core loss occurring to it. And the combination of this magnetizing current and IE will be referred to as no load current I naught. Why we are calling it no load current? Because if there is no current in the secondary circuit, then basically no current would be drawn. So if I2 is equal to 0 here, I1 dash should be equal to 0. Why? Because I1 dash by I2, that would be N2 by N1. So the two are related. So if one term is 0, another term would be 0. So whatever current is actually drawn from the supply side, having some voltage V1, so the I1 will be nothing but that would be equal to I naught only, because actually I1 would be the vector addition of I0 and I1 dash. Since this term would be equal to 0, so therefore I1 would be equal to I0, and therefore under such case we are referring this I0 as no load current. So whatever we have developed so far, this is basically the equivalent circuit of the transformer. This V2 is the voltage across the load. This E2 is the EMF developed in the secondary, and E1 EMF developed in the primary. V1 is the applied voltage, I1 is the current drawn from the primary side. That will have two portions, one meeting the core components, magnetizing current and loss component of current, and I1 dash, which is actually providing the current towards the secondary side. So this is what for today. I am stopping here. Thank you. Have a nice day.